Welcome to the TensorFlow.js workshop for Google I/O 2022. In this workshop, you'll learn how to create your very own simplified version of the popular Teachable Machine website to perform transfer learning with machine learning in JavaScript in the browser to recognize any object you desire. But what is this Teachable Machine website I speak of? Let's take a quick look at it in action.
People are training computers and creating machine learning models to explore all kinds of new ideas. New ways to interact.
Yes.
To understand the world. To play. And experiment. But machine learning is pretty intimidating to get into. So we've been wondering, what if it wasn't? With Teachable Machine, we set out to make it easier for anyone to create machine learning models without needing to write any machine learning code. When it first launched in 2017, it allowed everyone to get a feeling for what machine learning is all about. But now, Teachable Machine puts the power of machine learning in your hands, allowing you to save your models and use them in your own projects.
So let's say you want to build a model to recognize you versus your dog. You just open up the site, record samples of you, and samples of your dog. Click Train, and you instantly have your own machine learning model, which you can use in your sites, apps, and more. You can upload your model to host it online, or download it to work entirely on device.
With Teachable Machine, you can create custom models for all sorts of things. Using images, audio, or even poses. Personalized machine learning models for the things that matter to you. And folks have already been trying it out, using Teachable Machine in their own experiments, solving problems in their communities, or even just at home. Start creating and see where your ideas take you at g.co/teachablemachine.
Great! Now you know the end goal, it's time to open up my code lab that you'll use today to follow along. Head on over to codelabs.developers.google.com in a new browser window. And once the website's opened, search for TensorFlow.js Teachable Machine via the search box. You should then find a result titled Make Your Own Teachable Machine with TensorFlow.js in JavaScript as shown. Click on that. On the page that loads, you'll then see the sections of this workshop on the left, which you can use to follow along as I walk you through them live in this workshop video. So head on to step 2 as I teach you what TensorFlow.js is all about. So first off, what is TensorFlow.js? Well, if you're new to WebML, TensorFlow.js is Google's machine learning library for JavaScript, and it's just like the original version of TensorFlow that came out in Python, but is aimed at folk who code in JavaScript or Node.js instead. This allows more developers to use machine learning without having to learn a new language and use their creations in even more places than before, as JavaScript can run pretty much anywhere. From client-side to server-side, mobile native to desktop native, and even IoT devices like a Raspberry Pi, JavaScript is one of the few languages that can run in all of these locations without any additional dependencies. And currently, over 68% of professional developers use JavaScript in production. All of these users can potentially benefit from adding machine learning models to their web applications. And what are those benefits? Well, by running in the browser, you can achieve privacy as no sensor data needs to be sent to the cloud. Or how about lower latency for real-time performance with direct access to the device? And of course, lower costs as fewer server-side resources need to be kept running. You also get zero install for a frictionless end-user experience. You can use any of our demos in just one click of a link and reach an audience of billions instantly with no complex environment setup in a way people can share with ease. And if you're new to machine learning, we've just launched a brand new course for web and creative folk who are new to this industry but familiar with web technologies. Here you can go from zero to hero with machine learning in JavaScript and bring your creative ideas to life with TensorFlow.js. This course will teach you how to use machine learning in the browser to create next-generation web apps with superpowers from object recognition to text understanding and more. If you find this workshop too advanced, start with this course instead, and you can enroll today for free using the link on this slide and go at your own pace. But for those of you who already have used TensorFlow.js, let's demystify the process of transfer learning so we can make our very own teachable machine. Now head on to step 3 of the code lab. In its essence, transfer learning is all about taking the knowledge that has already been learnt to help learn a different but similar thing. And if you think about it, we as humans do this all the time. You have a lifetime of experiences contained in your brain that you can use to help recognize things you've never seen before. Take this willow tree for example. Depending where you are in the world, there's a chance you may have not seen this type of tree before. Yet, if I ask you to now tell me if there are any willow trees in this image, you can probably spot them pretty fast, even though they're at a different angle and slightly different to the one I originally showed you. Essentially, you already have a bunch of neurons that know how to identify tree-like objects and other neurons that are good at finding long straight lines. So you can reuse that knowledge to then classify a willow tree pretty fast, which is basically a tree-like object that has lots of long, liney branches in the vertical direction. So in a similar manner, if you have a machine learning model that's already trained on some domain like recognizing images, you can reuse it to perform a different but related task. In this case, you can do the same with an advanced model like MobileNet shown here. MobileNet is a very popular research model that's able to perform image recognition on 1,000 different object types. From dogs to cars, it was trained on a huge dataset known as ImageNet that has millions of labeled images. In fact, you can see in this animation here the huge number of layers it has in this MobileNet v1 model. Now during its training, it's already learned how to extract common features that matter for all of those 1,000 objects, and many of the lower level features it uses to identify such objects can be useful to detect new objects it's never seen before too. After all, everything is ultimately just a combination of lines, textures, and shapes. Now, if you could separate the pre-trained lower level layers of an existing trained model shown on the left from the classification layers near the end of the model shown on the right, which are sometimes referred to as the classification head of the model, you could then use these lower level layers to produce output features for any given image based on the original data it was trained on. Now, assuming the new thing you're trying to recognize can also make use of such output features, there is a good chance they can be reused for a new purpose. In the diagram shown, this hypothetical model was trained on digits, so maybe what's learned about digits can also be applied to letters like A, B, and C too. So now you could add a new classification head that's trying to predict A, B, or C instead as shown. In this instance, the lower level layers are frozen and are not trained. Only the new classification head will update itself to learn from the features provided from the pre-trained chopped up model on the left. The act of doing this is known as transfer learning, and that's what Teachable Machine does behind the scenes that you saw in action at the start of the workshop. You can also see that by only having to train the last few layers at the very end of a network, it will train much faster than if you had to train the whole model from scratch. So how can you get your hands on subparts of a model? Head on to step 4 of the code lab. Well, for more advanced research models like MobileNet, if you head on over to TensorFlow Hub at tfhub.dev and then filter for models suitable for TensorFlow.js that use the MobileNet v3 architecture, you'll find results like the ones shown on the slide. Now, some of these results are of type image classification, and others are of type image feature vector as shown. These image feature vector results are essentially the pre-chopped up versions of MobileNet that you can use to get the image feature vectors instead of the final classification. Models like this are often called base models, which you can then use to perform transfer learning. If you open up the page for one of these feature vector MobileNet v3 models, you can see from the JavaScript documentation that it's in the form of a graph model. It should be noted that if you find a model in the layers format instead of the graph format, you can choose which layers to freeze and which to unfreeze for training, which can give you even more options to fine-tune the model further. But what are the advantages of using transfer learning instead of training the whole model architecture from zero? Well, first, time of training is a key advantage of using a transfer learning approach, as you already have a trained base model to build upon. Secondly, you can get away with showing far fewer examples of the new thing you're trying to classify due to the prior training that's already taken place. This is really great if you've got limited time and resources to gather example data of the thing you want to classify and need to make a prototype quickly before gathering more training data to make it more robust. As such, given the need for less data and the speed of training a smaller network, transfer learning is less resource intensive, which makes it very suitable for the browser environment too, taking just tens of seconds on a modern machine instead of hours, days, or weeks for full model training. Alright, now you know the essence of what transfer learning is, it's time to create your very own version of Teachable Machine. Let's get started. Head on to step 5 of the Code Lab. Now head to glitch.com and open the TensorFlow.js boilerplate page by the link shown on the slide. Once loaded, fork a new copy of that you'll use to implement this project. You'll need to be signed into Glitch if you want to save your progress. Feel free to pause the video to do that and then continue. Now head on to step 6 of the Code Lab. In this section, you'll be replacing code in index.html. Go ahead and open that up and then replace the contents with the code on the following slides. The only part of index.html that you'll need to update is the content contained within the body tags as shown. Let's walk through the code. First, you'll add a heading and a paragraph tag with ID of status. This is where you'll print the information as you use different parts of a system to view the outputs. Next, a video element with ID of webcam is defined, to which you'll render the webcam later on. Moving further down the code, you can now define some buttons. The first with ID of enable cam will enable the web camera. The buttons with class data collector will allow you to gather example images for your classes of data. The code you write later will be designed such that you can add any number of these buttons and they'll work automatically as intended. Note that these buttons also have a special user-defined attribute called data-1hot with an integer value starting from 0 for the first class. This is the numerical index you'll use to represent a certain class's data by, as machine learning models like MobileNet must work with numbers and not strings. You can then use these numbers to encode the output classes correctly with a numerical representation instead of a string. There's also a data-name attribute that contains the human-readable name for this class, allowing you to provide a more meaningful name to the user to see instead of the numerical index value from the 1hot encoding. Next, you have a button to start training with an ID of train and a reset button with ID of reset that will clear all data so you can start over. Finally, you've got two script imports, one for TensorFlow.js and the other for your script.js that you'll define shortly. If you want to copy and paste the code directly, the completed index.html file is available at the URL shown. Now head on to step 7 of the Code Lab. Next, you can place contents in style.css to add style to your HTML elements. Here, some styles are added to position and size elements correctly. Nothing too special. You could certainly add to this later to make an even better UX like you saw in the Teachable Machine video. Again, if you want to copy the styles directly, the URL provided has a complete version of style.css to save time. Now, assuming you copied the HTML and CSS correctly, your live preview will now look like this, which contains the bare minimum user interface elements to make your very own Teachable Machine. Remember, after you complete this workshop, you may want to update the code to make the UX even better using your regular web engineering and design skills. Now head on to step 8 of the Code Lab. Okay, so next it's time to write the JavaScript code that will be contained within script.js. Go ahead, open that up and copy the code on the following slides as you go along. First, start by adding some key constants that you'll use throughout the app at the start of script.js. Let's walk through those. Status simply holds a reference to the paragraph tag you'll write status updates to, and video holds a reference to the HTML video element that will render the webcam feed. Next, you can grab references to all the key buttons from the HTML page. First, you have a button to enable the camera, a reset button to reset the app and start over, and a train button to begin training after data is gathered for each class. You can now define the expected input width and height for the MobileNet model. The one you'll be using expects an input image size of 224 by 224 pixels in size. By storing this in a constant near the top of the file like this, if you decide to use a different version later, it makes it easier to update the values once instead of having to replace it in many different places. Next, a constant called stopDataGather is defined and set to -1. Essentially, this stores a state value so you know when the user has stopped clicking a button to gather data from the webcam feed. By giving this a more meaningful name like this, it will make the code much more readable later on when you use it. Finally, you've got an array lookup called class names that holds the human readable names of the possible class predictions. This will be populated later. Okay, now that you've got references to the key elements, it's time to associate some event listeners to them. Start by adding click event handlers to key buttons. First, the enable cam button. It will call the enable cam function when clicked. Second, the train button that will call train and predict when clicked. And finally, the reset button that will call reset when clicked. These function skeletons are added at the end of this code to avoid errors and will be filled out later in the code lab. Next, you can find all buttons that have a class of data collector using document.querySelectorAll. This will return an array of elements found from the document that match. You can then iterate through the found buttons and associate 2 event listeners for each, one for mouse down and one for mouse up. This allows you to keep recording samples as long as the button is pressed, until the mouse button is no longer pressed, which will be useful for data collection. Both events will call a gather data for class function that you'll define later. At this point, you can also push the human readable class names from the HTML button attribute data-name to the class names array. Now, by using a class to find buttons here and not hard-coding a fixed number of data collector buttons, it allows you to change your HTML later to add more buttons, and the code will still function correctly for 3, 4, or any number of buttons like this. Next, add some variables to store key things that will be used later on. Let's walk through those. First, you've got a variable to store the loaded MobileNet model. Initially, set this to undefined. Next, you have a variable called gatherDataState. If a data collector button is pressed, this will change to be the one-hot ID of that button instead, as defined in the HTML, so you know what class of data you're collecting in that moment. Initially, set it to stop data gather, so the data gather loop that you'll define later will not gather any data when no buttons are being pressed. Video playing allows you to keep track if the webcam stream is successfully loaded and playing such that you can use it. Initially, this is set to false, as the webcam is not on until you press the enable cam button. Next, define 2 arrays, one for training data inputs and one for outputs. These will store the gathered training data values as you click the data collector buttons. Now, one more array is defined to keep track of how many examples are contained for each class once you start adding them. And finally, you've got a variable called predict that will control your prediction loop. This is set to false initially, and no predictions will take place until this is set to true later on. Now head on to step 9 of the code lab. Alright, all the key variables have been defined. Let's go and load the pre-chopped up MobileNet v3 model that will provide an image feature vector instead of classifications. First, define a new function called loadMobileNetFeatureModel as shown. This must be an async function, as the act of loading a model is asynchronous. Next, you can define the URL that the model you want to load is located at from the TF Hub documentation as shown. You can then actually load the model using await tf.loadGraphModel, remembering to set the special property from TF Hub to true as you are loading a model from this Google website. Remember, this is a special case only when using models hosted on TF Hub. Once loading is complete, you can set the status elements in a text with a message so you can visually see it's loaded correctly and you're ready to start gathering data. The only thing left to do now is to warm up the model. With larger models like this, the first time you use the model, it can take a moment to set everything up. Therefore, it's wise to pass zeros through the model once before you start using it elsewhere to avoid any waiting in the future when timing might be more critical. You can use tf.zeros with a batch size of 1 and a height and a width of the correct size that you defined in your constants. And finally, the color channels, which in this case is 3, as the model expects RGB images. You can then log the resulting shape of a tensor returned using answer.shape to help you understand the size of the image features this model produces. Finally, you can immediately call this created function to get the loading underway. If you view your live preview right now, after a few moments, you'll see the status text change from awaiting tfjs.load to become MobileNet v3 loaded successfully as shown. Ensure this works before continuing. You can also check the console output that will have printed the size of the output features that this model produces. After running zeros through the MobileNet model, you'll see a shape of 1024 printed. As the first item is just the batch size of 1, you can see it actually returns 1024 features that can then hopefully be used to help you classify new objects. Now head on to step 10 of the code lab. Okay, now it's time to start defining your model head, which is essentially a very minimal multi-layer perceptron. Start by defining a TF.sequential model to which you'll add layers to. Next, add a dense layer as the input layer to this model. This will have an input shape of 1024 as the outputs from the MobileNet v3 model features layer are of this size, as you saw in the previous step after passing zeros for it. This layer will have 128 neurons and use the ReLU activation function. If you're new to activation functions and model layers, consider taking the course detailed at the start of this workshop to understand what these properties do behind the scenes. Now you can add the output layer. Here, the number of neurons should equal the number of classes you're trying to predict. To do that, you can use classnames.length to find how many classes you're planning to classify, which is equal to the number of buttons found at the start of your code. As this is a classification problem, you'll use the softmax activation on this output layer, which must be used when trying to create a model to solve classification problems. At this point, you can print the model summary to the console to ensure everything is looking as expected. And finally, you can compile the model so it's ready to be trained. Here, the optimizer is set to Adam, and the loss will be either binary cross-entropy if the class names.length is equal to 2, else it will be categorical cross-entropy if there are 3 or more classes to classify. Accuracy metrics can also be requested so they can be monitored in the logs later for debugging purposes. At this point, if you check your console output, you'll see the following printed. Note that this has over 130,000 trainable parameters, but as this is just a simple dense layer of regular neurons, it will train pretty fast. Now you could try changing the number of neurons in the first layer to see how low you can make it while still getting decent performance. I'll leave that for you as an activity to do once you complete the project. Often, with machine learning, there's some level of trial and error to find the optimal parameter values that you give to the model for the best trade-off between resource usage and speed. Now head on to step 11 of the code lab. Alright, next you can create a function to check if the browser supports getUserMedia by checking the browser's APIs that are available. Once defined, you can flesh out the enableCam function. First check if getUserMedia is supported using the function you just defined above. If it isn't, you can print a warning to the console. Next, define some constraints for your getUserMedia call. In this case, you also specify that you prefer the width of the video to be 640 and the height to be 480 pixels. Why? Well, there's not much point getting a video larger than this, as you'll need to be resizing this to 224 by 224 anyhow to be fed into the MobileNet model, so you may as well save some computing resources by requesting a smaller resolution. Most cameras support a resolution of this size. You can then call navigator.mediadevices.getUserMedia with the constraints above, and then wait for the stream to be returned, at which point you can get your video element to play the stream and add an event listener for the stream load. In this instance, once the stream loads, you can set video playing to true and remove the enableCam button to prevent it from being clicked again by setting its class to be removed. If you run the code at this point and click the Enable Camera button and allow access to the webcam if it's your first time, you should then see yourself rendered to the video element on the page as shown. Okay, now it's time to add a function to deal with the data collector button clicks. Head on to step 12 of the code lab. Define a new function called GatherDataForClass as shown, which is what you assigned as your event handler function at the start of this lesson. You can now check the data-1hot attribute on the currently clicked button by calling this.getAttribute with the attribute's name, in this case data-1hot as the parameter. As this is a string, you can use parseInt to cast it to an integer and assign this result to a variable named class number. Now you can set the gather data state accordingly. If the current gather data state is equal to stop data gather, which you set to be -1, that means you're not currently gathering any data, and this was a mouse down event that fired. Therefore, you want to set the gather data state to be the class number you just found from the button attribute. Otherwise, it means you are currently already gathering data, and the event that fired must have been a mouse up event, meaning that you now want to stop gathering data for that class, so you can just set it back to be the stop data gather state, which will end the data gathering loop that you'll define shortly. Finally, you can kick off the data gather loop that will actually perform the recording of class data. Alright, so let's head on to step 13 to see how to do that. Naturally, now it's time to define the data gather loop function. This function is responsible for sampling images from the webcam video, passing them through the MobileNet model, and capturing the outputs of that model, which is the 1024 feature vectors. It will then store them along with the GatherDataState ID of the button that is currently being pressed, so you know what class these feature vectors represent. Let's walk through it. First off, you're only going to continue if video playing is true, meaning that the webcam is active and GatherDataState is not equal to stopDataGather, meaning a button for class data gathering is currently being pressed. Next, wrap your code in a tf.tidy to dispose of any created tensors in the code that follows efficiently. The result of this tf.tidy code execution will be stored in a variable called ImageFeatures. Now you can grab a frame of the webcam video using tf.browser.fromPixels. The resulting tensor containing the image data will be stored in a variable called videoFrameAsTensor. Next, you can resize the videoFrameAsTensor variable to be of the correct shape for the MobileNet's input. Here you can use a tf.image.resizeByLinear call with the tensor you want to reshape as the first parameter, and then a shape that defines the new height and width you require, which are defined by the constants you already created at the start of this lesson. Finally, set align corners to true in the third parameter to avoid any alignment issues when resizing. The result of this resize is stored in a variable called resizeTensorFrame. Clearly, this will stretch the image as your webcam image is 640 by 480 pixels in size and the model needs a square image of 224 by 224 pixels. For the purpose of this demo, this should work fine. However, once you complete this lesson, you might want to try and crop a square from the image instead for even better results for any production system you might create. Next, you must normalize the image data. Image data is always in the range of 0 to 255 when using tf.browser.fromPixels. That means, in this case, you can simply divide resizeTensorFrame by 255 to ensure all values are between 0 and 1 instead, which is what the MobileNet model expects as inputs. Finally, you can push this normalized tensor through MobileNet by calling MobileNet.predict, to which you pass the expanded version of the normalized tensor frame using expandIms, so it becomes a batch of 1 as the model expects a batch of inputs for processing. Once the result comes back, you can then immediately call squeeze on that to squash it back down to a 1D tensor, which then return and assign to image features that captures the result from tf.tidy. Now that you've got the image features from MobileNet, you can record them by pushing them onto your training data inputs array that you previously defined. In a similar fashion, you can also record what this input represents by pushing the current GatherDataState to the training data outputs array too. Note here that the GatherDataState variable would have been set to the current class's numerical ID that you're recording data for when the button was clicked in the previously defined GatherDataForClass function. At this point, you can also increment the number of examples you have for a given class. To do this, first check if the index within the examples count array has been initialized before or not. If it's undefined, you can simply set it to 0 to initialize the counter for a given class's numerical ID. You can then simply increment the examples count for the current GatherDataState. Finally, you can update the status text on the web page to show the current counts for each class as they're captured. To do this, you can just loop through the class names array and then print the human readable name combined with the data count at the same index in examples count. Last but not least, call window.requestAnimationFrame with dataGatherLoop passed as a parameter to recursively call this function all over again. This will continue to sample frames from the video until the button mouse up is detected and GatherDataState becomes stopDataGather, at which point the dataGather loop will end. Okay, if you run your code at this point, you should be able to click the Enable Camera button, await the webcam to load, and then click and hold each of the Gather Data buttons to gather examples for each class. Here you can see me gather data for my mobile phone and my hand respectively. You should then see the status text updated accordingly as it stores the tensors in memory as shown on this slide. Okay, now head on to step 14 of the code lab. The next step is to implement your train and predict function, which is where the transfer learning actually takes place. First, ensure you stop any current predictions from taking place by setting predict to false. Next, shuffle your input and output arrays to ensure order does not cause any issues in training. Now you can convert your outputs array to be a tensor 1D of type int32 so it's ready to be used in a one-hot encoding. This is stored in a variable named outputs as tensor. You can then use the tf.oneHot function with its outputs as tensor variable, along with the max number of classes to encode, which is just the class names.length. Your oneHot encoded outputs are now stored in a new tensor called oneHot outputs. Now currently, training data inputs is an array of tensors. In order to use these for training, you'll need to convert the array of tensors to become a regular 2D tensor. To do that, there's a neat function within the TensorFlow.js library called tf.stack, which, as you may have guessed, takes an array of tensors and stacks them together to produce a tensor as an output instead. In this case, a tensor 2D is returned, which is what you need for training a batch of one-dimensional inputs that are each 1024 in length, containing the features recorded. Next, you can await model.fit to train the model. Here, you can now pass your inputs as tensor variable along with the oneHot outputs. And in the configuration object, set shuffle to true, use a batch size of 5 with 10 epochs, and of course specify a callback for onEpochEnd to the log progress function that's defined at the end. Finally, in this function, you can dispose of the created tensors as the model is now trained. You can then set predict back to true to allow predictions to take place again, and then call the predict loop function to start predicting live webcam images. Now at this point, you can also define the log process function to log the state of the training, which is used in model.fit above that will print results to the console after each round of training. Alright, you're almost there. Time to add the predict loop function to make predictions. First, check that predict is true so that predictions are only made after the model is trained and available to use. Next, you can get the image features for the current image just like you did in the data gather loop function. Essentially, you grab a frame from the webcam using tf.browser.fromPixels, normalize it, resize it to be 224 by 224 pixels in size, and then pass that data through the MobileNet model to get the resulting image features. Now, however, you can use your newly trained model head to actually perform a prediction by passing the resulting image features just found through the newly trained model head's predict function. You can then squeeze the resulting tensor to make it one-dimensional again and assign it to a variable called prediction. With this prediction, you can find the index that has the highest value using argmax and then converting this resulting tensor to an array using arraysync. This value is stored in the variable called highestIndex. Next, you can also get the actual prediction confidence scores in the same manner by calling arraysync on that tensor directly too. You now have everything you need to update the status text with the predictions. To get the human readable string for the class, you can just look up the highest index in the class names array and then grab the confidence value from the prediction array in the same manner. To make it more readable, as a percentage, just multiply by 100 and math.floor the result. Finally, you can use window.requestAnimationFrame to call prediction loop all over again once ready to get real-time classification on your video stream. This will continue until predict is set to false if you choose to train a new model with new data. Which brings you to the final piece of the puzzle, implementing the reset button. Head on to step 15 of the code lab. First, stop any running prediction loops by setting predict to false. Next, you can delete all contents in the example's count array by setting its length to 0, which is a handy way to clear all contents from an array. Now go through all the current recorded training data inputs and ensure you dispose of each tensor contained within it to free up memory again, as tensors are not cleaned up by the JavaScript garbage collector. Now you can safely set the array length to 0 on both the training data inputs and training data outputs arrays to clear those too. And note that if you had set the length to 0 on training data inputs before disposing the tensors would be unreachable but still in memory and not disposed of, which would be very bad as this would cause a memory leak. Finally, set the status text to something sensible and print out the tensors left in memory as a sanity check. It should be noted that there'll be a few hundred tensors still in memory, as both the MobileNet model and the multi-layer perceptron you defined are not disposed of, as you'll need to reuse them with new training data if you decide to train again after this reset. Alright, now head on to step 16 of the code lab. Okay, now it's time to test out your very own version of Teachable Machine. Head to the live preview, enable the webcam, gather at least 30 samples for class 1 for some object in your room, and then do the same for class 2 for a different object. Hit train and check the console log to see progress. It should train pretty fast, and once trained, show the object to the camera to get live predictions that will be printed to the status text area on the web page near the top. If you're having trouble, check my completed working code on the link shown to see if you missed copying over anything. Finally, head on to step 17 of the code lab. Congratulations! You just completed your very first transfer learning example using TensorFlow.js live in the browser. Remember to try it out and test it on a variety of objects. You may notice some things are harder to recognize than others, especially if they're similar to something else. You might need to add more classes of data or more training data to be able to tell them apart. Now, in this code lab, you learnt what transfer learning is and its advantages over training a full model from scratch. You also now know how to obtain models for reuse from TensorFlow Hub, and how to set up a web app suitable for transfer learning. You also learnt how to load and use a base model to generate image features, and then how to train a new prediction head that can recognize custom objects from webcam imagery, which was then used to classify data in real time. If you're new to TensorFlow.js and want to understand deeper what some of the options and terminology in this workshop represent, you may want to consider taking my Zero to Hero course that assumes no prior knowledge in machine learning and will teach you everything from a blank canvas, as this workshop was aimed at intermediate users of a TensorFlow.js library who are already familiar with tensors and our APIs. But now, with these superpowers, you can recognize any object you wish in your own web apps. And what problems in your life could you use this for? Maybe you can launch a video when you recognize a brand's new product. Or maybe you can recognize when your car is in front of the garage and use a Raspberry Pi to open the door automatically. The possibilities are endless. If you make something using TensorFlow.js, be sure to tag it with the hashtag MadeWithTFJS on social so we can find your work for a chance to be featured on the TensorFlow YouTube channel. Thanks for listening, and I'll see you next time.